Welcome back, everyone, to another edition of Dell's Rails, where this is the second in a series of videos I'm doing for the transformers for your layout. And this particular setup I have here, I thought while I had this out is to go ahead and do a video on how to phase your transformers with a meter. I'm going to use a meter. And I've got these two transformers, and you can see the meter over here. It's on and running already. It's already set to the voltage. And then both transformers, it's an advantage that they just happen to be identical, so that's kind of an advantage. And then also, I like using the variable post, so I am using the AUs and AUs for testing purposes on this transformer. You could use other ones. I just like using the variable because I can actually dial in with my meter here a precise voltage to know how much voltage. So if I want exactly 8 volts or close to that, I can get it here and I can get it there. I am using the 0 or the 5 to 16 volt variable setting on both transformers. And so what I did is I dialed both transformers approximately to around 8 volts. It's hard to get them exact, but for demonstration purposes, it's easier to show this because if these transformers are in phase, and there's no way to know if they are until you test them like this, if they're in phase, then the reading I would expect to get would be something pretty close to 0 because I've got my settings 8 volts. So it's safe to say 16 volts and 60. If they're out of phase, I might see something as high as 16 volts. Now, maybe the 8 volt setting, I just used that because it was half of 16, may not have been the best setting to use. Maybe I should have went off a little more because if you see 16 volts, it might look okay because it's 16 volts. But I know that these are both set to 8 volts, so I know that wouldn't be right if I seen 16 volts to think that they were in phase. But even if you know what you're doing, that could be a little confusing. So I would probably recommend going one way from one way of center of 16 volts there, say maybe 6 or 10. So the bottom line is, if you got the transformers in phase with these settings, you should read something on your meter pretty close to 0 if they're in phase. And if they're out of phase, it's going to be double of this setting. So that's generally the rule of thumb. It doesn't always work like that, though. I'll let you know if you're using a solid-state electronic transformer phased with one of these coil and core winding type transformers. So it's good to show it to you with these two identical transformers. So I'm glad I had this to be able to do. So I'm going to test this real quick. Both transformers, like I say, are plugged in. They're working. I've got the U posts on both transformers. I have no clue which is which, but you got to start somewhere. You kind of have a 50-50 chance here, so these could be in phase and they may not be in phase. We just don't know, but you need to start somewhere, so tie your two posts that are the same, like both A's or both U's. You just interconnect between two transformers, the same corresponding post you're on. And it won't matter if it's out of phase because we'll show you how to change that. So now, since I've got U to U, I'm going to check from A to A with my meter across there. So if I go to A, we look over that meter, it should be pretty close to 0, and look at that, it's 0.244. So I'm going to say these transformers are in phase. So how do we change that if they weren't in phase? Well, you could swap these two wires. And when I talk to you about color coding could get you in trouble, this is why I phase my transformers with my CW80, because it does have the polarity corrected on the version that I'm using. So my black wire is my black wire, my red wire is my red wire on that transformer. That's why it's good to have your CW80s. That way I can show you how to make sure you can phase your other transformers, especially your post-war style, with your CW80 to ensure that your U terminal on that transformer will always be U and your A will always be A. So the easy way to do that, you can do it two ways. We can switch these two wires around on any one of these transformers and they would be back in phase. Or the preferred method I use is to, if you've got these older transformers, The CW80, by the way, you can't do this because it does have a 2-prong plug on there, but it is polarized. But these older post-war transformers are not polarized. That's why you don't really know which is which on these terminals. And so the easy way to change this, I'll go over here and show you, we just simply unplug this, one of these, turn that plug 180 degrees, and now plug it back in, because that plug on there is not polarized. Now when I test this between A and A again, we should see something close to double 8 volts, something like 16. See over there? 16.87. Now I know these transformers are out of phase, but let's say I wanted to make this my black and that my black, this my red and that my red. I want them to match so that when they go tie under my layout, I'm not out there tying a black to a red and vice versa. So color coding is important, but that's what I want to point out. It can get you in trouble when you're thinking in terms. It's better, you know, to train you as an electrician from a standpoint as to what it's actually occurring on the wire, not what the color is. That's what it's first and foremost for safety. You know, they train young guys too much about color coding, and they beat that into them so much, and it's not bad, but it can get them in trouble. They need to think in terms of what voltage is present on those wires, because this wire doesn't care if it's black or red. It's going to carry whatever you put across it. And so as professionals, we tend to run into stuff like that, even if other professionals have been there before us and done the installation. Even if they're professional, they don't always install correctly. So I'm going to reverse this back. We just simply, we know we changed this one. And then when you do that, I would recommend getting some type of identification, maybe even a silver magic Sharpie, and just take, we know that the wide slot on our polarized is the wide slot on this receptacle, because one's wide and one's skinny. Well, the wider of the two is always the common grounded conductor. Not grounding, but grounded common conductor. And when I was showing you about these cords, well, they identify with something, either a ribbed or maybe even, it could even be writing, you know. That's why they identify that cord. So that's important. When you tie this back in, you tie it back in the same way. Like I said, it doesn't really matter because you got a non-polarized plug on there. But it's good to match it up. You can see how easy it is to change. Now that would be the thing, maybe to find a new cord and put a polarized one on, and then figure out where these wires are landed to ensure that your transformers stay the same. Or you could simply just go get, and I would recommend a silver mat because a black isn't going to show up, and just, you know, color around that prong. That way you'll remember if it ever comes unplugged to know how it was in there originally. And also, you know, like I said, your railroad can change as you grow, because every transformer you drag over there is going to be different, unless it's probably a modern solid state that has a polarized plug on it. And that's why I thought it was important to polarize my layout with a solid state transformer that I knew that it had established the colors correctly. So now I know I'm back. These two transformers are phased. I could put this out. The advantage of this is I could just loop these two wires together, and I could come off here with one wire and run out there and feed everything under my layout with one neutral wire. I don't have to run. It saves a bunch of wire, and it saves a lot of confusion. I don't have to run combinations of neutral conductors or common conductors out there under my layout. And everything on my layout, whether it's lighting, the outside rails of my track, signals, they're all tied to that common bus ground. It makes it a lot simpler to do the bus wiring under your layout, just because all your connections under your layout are just done by small, maybe 1-2 foot at sections of length of wires at the most. That way you can run a lot bigger feeder, like a 16 gauge under your layout, and drop down underneath there with a 1 or 2 foot section of 18 gauge wire and tap to that. Because it gets kind of difficult to try to find terminals and stuff like that for all those different ranges of wires that you might run across while you're doing this. And I find for the most part, 16 gauge is pretty good for most average size, standard size layouts. You get into a really large layout, you might need to start going to a little bit more robust wire gauge. But 16 gauge AWG, most transformers, are set up probably, like the ZW over there, that older post-war. It does have a 15 amp fuse in it. And the 16 AWG, for safety reasons, I would say is plenty acceptable. It's all relative to the insulation, by the way, and how long you run it, how much amperage it will carry. But I'm going by a standard size layout here. Just keep that in mind. So 16 AWG, I would say a safe amperage to carry on there is about 10 amps. Your 18 AWG is 5 amps. And those two are usually the size amperages that we're dealing out there in the layout as far as power to your track. That ZW does have the capacity to carry 15 amps. But the whole transformer is figured at 15 amps. And we'll get into that too, why it's not a good idea to rely on the internal fusing as a sole fusing for that transformer for this reason. Now, I'll cover that too. I want to clarify something real quick. I said in the last video, I left the impression that this polarity on this transformer cannot be reversed by the wall outlet. You can. It will reverse the polarity. But the issue I had was that this transformer was already phased with my other transformers to work off the variable voltage setting. It wasn't until I tied into this fixed that it caused the problem. And it was already phased, so it threw it out of phase by tying this in somehow. And so I had to do the connection here on the transformer and reverse it, which caused my color coding to be reversed of my other transformers. Now, I'd rather do that here at the transformer than under the layout. I want all my colors to match there, and just, if I bring in another transformer, I can just do it real easy at the transformer. Phase the new transformer. Saying that, this particular transformer, this 1033, is probably not the best transformer to use when phasing with other transformers, unless you're phasing it with another 1033, and then you can you'll probably be all right. I don't know. I haven't checked all the terminals, but you want to check me out on that first. But so if you're running that problem, I don't know if even if these were phased, if this transformer is still going to have a problem between the transformers having a common connection when you're starting to use both the fixed and the variable setting on this transformer. So I wanted to clarify that, and thought that was important to point out. The other thing I wanted to cover real quick here is the transformers themselves, like which transformer is best for my layout. So specifically these older core and coil post-war style versus a solid state electronics. When you're considering a transformer for your power needs, which one really is best for my application. So the post-war's advantages are they're a more robust design. Meaning this transformer has stood the test of time. It's been around for 70 years or better, and it's probably going to be around for that long again. I don't know if you're going to be able to say that about any modern solid-state electronic, even produced today, that it'll be here in 70 years. And if you don't believe me, just take these out to a gun range and try to put a bullet through them and see which one stops the bullet. This transformer usually costs per watt of power produced. So it's cheaper usually to buy up front this 90 watt transformer than say a CW80. I mean, just depends where you buy stuff. You might be able to run across some deals. This this transformer, the big advantage in my regards, in my opinion, is it produces a very clean linear 60 hertz sine wave. For those of you that I've heard talk about, well, these are going to destroy your solid state electronic motor just because they have all these surges. Well, I'm not sure what type of surges. When somebody says that they're talking about, there's power surges, and then there's TVSS surge. So if you're concerned about TVSS, it's actually your solid state design transformers that produce harmful transient voltage surges that actually can destroy the boards in your locomotives. Because it's a nonlinear load. Because of its solid state circuitry design, meaning it's using capacitors, rectifiers, and diodes in there to convert AC to DC and all that. Well, that's what they call DC switching, and that's what creates harmonic loading on your AC circuit line that electronics don't like. So the other big advantage to this transformer is they're easy to retrofit and upgrade to modern circuit design. For protection to this transformer or your locomotives on it. So you can buy a solid state, quick break, auto resetting circuit breaker and diodes for your control, for your control and sounds on your locomotive. The disadvantages, of course, is age. I would recommend doing a visual inspection on these if you're trained to know kind of what to look for. Usually I rely heavier on that than anything else. And then also take a meter and check these voltages out. You certainly want to do that. Do a visual inspection. See if somebody's been in there monkeying around with it like I just did. And if you're trained, I've been in there. I would know I've been in this. And if you're concerned about it, you can use a mega ohm meter. I have never been a strong proponent of using a mega ohm meter on stuff this old. I mean, you could destroy it just hitting this stuff with its maximum mega ohm. So to me, that's up to you. If you want to use a mega ohm meter on, I'm all for it. But if I'm selling one of these to you, I don't know if I want you to mega ohm it. So safety in that regard is the other disadvantage of transformer due to the fact of the aging fusing in them and it's very antiquated means of fusing. But as you see here, easy to retrofit these. Another big disadvantage of this transformer due to this design, it's less efficient use of power. So saying that, this transformer has a power factor, probably conservatively speaking, probably 0.8. So you're looking at about 80% power efficiency. So you're paying for 90 watts of power. That's what it says here off your electric bill, but you're not going to be getting 90 watts. I can guarantee you're not getting 90 watts off of this tap out to your layout. You do the math on that, 80% of 90 is 72. So in that regard, this transformer is actually less wattage than the CW80 at 90 watts of power. So that's something to factor, and it's probably much less due to the variable factors like aging and installation and condition of locomotives. One thing that creates this overheating is the fact that you got either poor track installation, loose track joints, loose wire connections, down to as little as it's not properly lubricated to run at its optimum efficiency. All contributes to these post-war transformers, to the efficiency of this transformer of delivering power to your layout. The problem with these transformers, once they start heating up, these by code, we would consider this a continuous load, meaning it can operate for 3 hours straight or longer. Now you're going to say, well, I ain't going to run my train for 3 hours straight. doesn't matter if you can or not. I can plug this in and walk away from with it plugged in, even though my trains aren't running for 3 hours or long, if you forget to unplug it. So this is considered a continuous load, and by that, it's gonna eventually start losing power due to the efficiency of power loss. That's why you can probably run your trains for a while and then step away from the layout and come back, and they've either slowed down or stopped altogether, and you're kind of scratching your head. Well, that's because when this starts heating up, it starts losing power. So that's a disadvantage over the solid state electronic transformer. Now, the advantages of the solid state is the improved efficiency. It has a power factor of 1. It's 100% efficient due to its solid state circuitry design. That's how they solved that problem. They used solid state electronic circuitry to solve the problem of transformer inefficiency. By doing so, though, the trade-off was transient voltage surges. So it has a proven efficiency, meaning if whatever watt produced, that's how much watt it's capable of delivering. So an 80 watt CW over there, you're paying 80 watts off your electric bill, you're getting 80 watts out to your track. It's probably a little cheaper to even run your trains if you got apples to apples. Although I don't know if it's enough to see a big reflection in your electric bill, so I wouldn't get too excited. The solid state circuitry design that leads to the improved efficiency is cheaper to operate. It's safer, better, quicker reacting fusing in your solid state transformers. The disadvantage of those solid state transformers like the CW80 is they're more expensive per watt produced. They produce a nonlinear chopped sine waveform, which means transient voltage surges. Solid state electronics, while more efficient, producing a nonlinear waveform, or TVS, due to their design using solid state electronic capacitors, diodes, and rectifiers, which leads to increasing the efficiency to a power factor of 1, are also prone to deliver transient voltage surges that contribute to component damage not experienced by the linear loads of a core and core post-war transformer. You could say, while being more efficient, in a way, they are their own worst enemy when it comes to life expectancy. Solid state DC switching that occurs in electronic devices is what causes TVS harmonics. This is a primary cause for PC chip or electronic circuit degradation that ultimately leads to failure of electronic devices. This phenomena occurs at light speed and is like cancer to the chips that ultimately lead to failure. So that locomotive that you got running out there, it may not be dead yet, but it's dying, I guarantee you, because it's just a matter of time before all that stuff fails. That's what I mean, like it's cancer to your locomotive. So knowing that, you probably want to provide transient voltage surge if that manufacturer hasn't provided it in their equipment. And even if they have, I would question just how good that transient voltage surge is. Typically, transient voltage surge suppressors for solid state electronic equipment tends to be the most expensive surge out there that you can buy. In other words, a lightning arrestor won't do it. It really needs to be something for transient voltage surges. So I can see where some people might have some reservations of tying this to their locomotives, solid state locomotives, frying them. It's more from power surges, not from transient voltage surges. So the thing of it is, when you're running your solid state electronics, doesn't matter what it is, the transformer, the train, when you're running that, there's surge currents going on all the time while that's under power. So that's really more the surge you need to be concerned about. Yeah, you could have a short out there on the track and have a serious power surge and blow stuff up that way, but maybe that was just the final nail in the coffin of what the transient voltages had already started. So what I came to the conclusion of, in a nutshell, your post-war transformer strengths is the solid-state electronics transformer's weakness, and vice versa. So there's good pros and cons about both. That's why I thought it was good to bring this to your attention, and hopefully you gained enough information a little bit to be a little bit more informed of what it is you might need to be looking for when you're powering your layout. For this next topic, I thought it was good to come over here to the layout and it'd be easier to show you this. This is the retrofit I did for this transformer, upgraded, the fusing. But the thing I wanted to point out here on this transformer is that a 15 amp fuse is protecting this whole 275 watt transformer. So the concern would be you've got these separate circuits or zones off of each transformer, because this transformer has 4 separate variable posts. So you're essentially fusing each one of these for 15 amp. Now, are you using that much power out here to the layout on each one? Not hardly. So that would be the concern. I would provide supplemental fusing. You can put it here. I've got a terminal strip up underneath my layout. It's kind of the purpose I use that to make changes and adds and stuff like that. So you can set it up however you want for yours. It doesn't matter as long as you provide fusing. But they do have fusing you can add here off the back of each one of these individual zones. And also, in addition, probably a good idea to add TVSS. Just to give you an idea of what I'm talking about here, take, for instance, my breaker box. Instead of having an individual circuit breaker for each zone of protection here, I'd be fusing every circuit in here off of this one 200 amp main breaker. So that's kind of what you got going on here with this transformer. So that would be the concern if any of you guys are running these multi-zone transformers that are under single fusing. I did kind of look into a newer style ZWL, and just to kind of see what kind of power that thing is putting out, and that's impressive. You guys can say what you will about Lionel, but man, anybody that puts out something like that for your toy train transformers, I'm not saying anything bad about them. But then again, I don't buy new stuff anyway, so it doesn't affect me. So this ZWL, it's crazy. That thing is a 620 watt transformer as opposed to 270 watts of power here. I mean, what that works out to, figured it at 18 volts, that's 35 amps. That's just crazy to me. I mean, amps are amps. I don't care if they're low voltage amps or if they're high voltage amps. When I say high voltage, like where I worked, 120 and above. So that's the amperage of a 240 volt clothes dryer in your house. So that's how crazy that is. So it's pretty remarkable. It's 180 watts. It provides, unlike this transformer, it is limited to 180 watts per output. Now, that's a 10 amp at each post. Now, it won't deliver 10 amps to each one, but it has a potential to, if that makes any sense. So it is equipped with what Lionel calls their dynamic power sharing, meaning that power output can automatically be diverted seamlessly to any one post as the demand calls for it. So if you got some trains running, all of a sudden it needs more power on this post, it just automatically compensates for that. So yeah, say what you want about Lionel, but that's impressive. And that's for your toy trains. That's kind of the level of sophistication they went for your toy trains. So that transformer may be fused up a little different. That's why I kind of looked into it, but this one certainly isn't. So I would highly recommend, if you've got a ZW like this with multiple zones on it, you want to look into not only surge, but also protection. When you're putting the TVS surge on, just so you know, you're not really doing that for overload. You're really doing it, the minute it's put in, it's doing a job. It isn't just waiting for a short to occur. It's not really designed for that. It's really to clamp on and suppress harmful, unwanted surge currents produced by transient voltage surge, actually produced by your solid state transformer that could be going in there and hitting the chips on your locomotives. Hey, real quick, almost forgot here to tell you about my phenomena that went on, but what I was doing, I had this set up here, really to shoot my regular scheduled video I do on Fridays for this new arrival that I just bought. And had the 736 with this tender set up, running. And, it got to this curve here, and that's when something happened. It derailed or something. Then I remember putting it back on the track and then powered it up, and it takes off, and it's running just fine. But the whistle tender is sounding. And I couldn't understand what was going on. And, so on this transformer down here, and like I said, I worked on it. That's this loop that engine's sitting on. And, the whistle tender just wasn't going off. I wish I would have videotaped this while it was occurring, but it didn't occur to me to, because I was so puzzled as to what was going on because I could not figure it out. It was, I did everything that you would think of. I put different tenders on there, post-war tenders, and they all did the same thing. Ironically, the only thing that worked okay was anything with rail sounds. This tender here had rail sounds on it, so I stuck it on there, and it worked just fine, like it normally would with that whistle button on the transformer there. And as soon as I put the post-war tender back on and turn the transformer on, it would be going off. And so I think what I had, and I did just about everything you could think of. I took this cover off. I cleaned the contacts. I shot contact cleaner, shot everything down, and nothing. It just kept working. And then I think I seen somewhere, it was kind of weird. It was almost as if the E unit could be responsible for this. And I did take the engine apart when I seen that, and that's when I seen a bad E unit. And so the E unit was bad, but it led me to believe that a bad E unit could cause this. And maybe what I had was what they call that DC offset, and but not really knowing anyway how to correct it. And so, I did everything possible. And of course, I had this transformer turned on and off several times while I was working on it, and it never did reset it that way. So what I did was, just to show you what I did, and it cleared it, and I don't know why this would do it, but I'm just going to show you what I did. I took this transformer here and tipped it over like that, and just to check to see if I swapped this track with that track with my transformer wiring. And that's what I did. I interchanged these two and tried it. Well, suddenly, both sides worked like they were supposed to. So I switched it back. And it's been working fine ever since. So that's all I did, was physically take these two outside posts off and switch and flip-flop them and flip-flopped them back. I mean, the minute I flip-flopped them, everything worked fine. And that was just a real head scratcher to me. So I thought that was kind of interesting to point out to you in case you run across that. I don't know if that's going to be your situation. And I don't know. It's either that or I got some train ghost down here that thinks I need to have material for video. So there you go. I thought that was worth sharing. I took some readings here for you guys, amperage readings, but I got to think about it. It might be just a little bit more fun to show this to you. I know I'm kind of weird that way. I think that's fun, so you're just gonna have to bear with me. Well, hold on a minute. I think I just heard something outside my front. I'm expecting a delivery. Got something new coming for you guys. I'm kind of excited about. So let me go. Holy cow! I had to show you guys this. Look at the size of that box that showed up at my door. No wonder I had to pay so much for shipping. I didn't know I was buying a train and patio furniture. Well, this was supposed to be the subject of this week's video, so please stay tuned. I'm still planning on getting that out, and I'll show you what I got. Okay, back to our show. Boy, that was a really big box. Well, I wasn't expecting that, and hope I didn't get you guys all excited for nothing. It's not that big of a deal, but it's kind of neat. I'm really excited about it, and I want to, give a shout out to Uncle Salty. He's kind of was the inspiration for me to kind of pull the trigger on this purchase. And it's not quite what we talked about, Matt, but it is at manufacturer, and you probably won't be all that impressed with it, but I'm kind of excited about it. And what I thought I'd show here, instead of just kind of revealing to you my findings, I thought it'd be kind of fun to really see what these amperages are real time with this engine running. So let's get it running around here. I think I'll start it out about 14 volts. See, we're already jumped up about 4 3/4 amps. And you can see it's not really running all that fast. We'll get her cranked up here a little bit more. There's 18. See what we're doing here at 18. Not quite 5 1/4. A little over 5 amp right there at 18 volts. We'll just go ahead and crank her on up. So flat out, she's running about 5 1/2 amps. Once it smooths out, she drops off a little bit. So there it is running 5.3. You can see this engine's geared slow enough, it ain't gonna fly off the table, so. And I'm not suggesting you're going to run your engines that fast. It's just the reason I'm showing that is, calculations are usually taken at their maximum value for fusing purposes. So that's kind of what this is for. And, hopefully this gives you some kind of a determination or an idea of what maybe be a good fuse to size this. I certainly think 5 would not be enough, because you can see that's going to be a problem. So, I'm not sure what your availability and ranges you're going to get. This comes with a 15 amp already. I think that's a little high. So somewhere maybe around 10 would be good. It just depends on, if you start double heading, that's going to enter into, and I tried to find a locomotive that I knew was going to, draw the most power possible. So this is it. I could have probably threw some more passenger cars on there. And just to give you an idea, those passenger cars, there's 5 of them. They got 2 light bulbs each. They do have the older bayonet-based bulbs. They were only like 1.4 watts. So the math's real easy on that. They don't add that much load, really, even these incandescent lamp locomotives. You're looking at an amp to run those 5 passenger cars. As compared to the engine, which you're looking at 4 1/2 amps. So this is where your load is, right here. I mean, you're looking at the combine here. That engine there does have a light bulb in it. I got rail sounds on, but the rail sounds doesn't really draw much. I've checked that out. It draws about 0.30 watts. So you're looking at minuscule amps on that. And most of the load is going to be in those passenger cars and your engine, so or anything with lights in it. And yeah, that one engine adds a light, so you're adding maybe another 1.4 watts of power. I was kind of surprised that those light bulbs weren't higher wattage than that, but that's kind of what the math works out to. And I stuck the GG1 on here, took this 2343 engine off. I left the rest of the consist as it was just to get a comparison, and it was drawing like an amp less. So even your dual can motored engines like your Williams and your Lionels and MTH, K-Line, not these over here that's got the small can motors in it, but I'm talking about the larger can motored engines. The difference between it and this, it was only like an amp difference. So that gives you kind of an idea of what you're going to run into if you're trying to do some fusing on here. And that's what this was intended to do, to kind of bring it to your attention that supplemental fusing off your individual zones there would probably be a good idea. Well, that's all I had for this week's episode. I sure hope you guys enjoyed it. Look forward to my unboxing on my new arrival, and I'll be releasing that this week yet too. So thanks for watching, everyone, and have a great day. You're watching Dale's Rails.